get started.
Hi, so our group is called Smart Sleep. Our project is a smarter baby sleep system for sudden infant death syndrome monitoring. So our goal is that we want to design an advanced baby sleeping monitor that can help prevent the chance of SIDS. And SIDS is the sudden and unexplained death of a baby within their first 1 to 2 years of life. So current research on SIDS details that the convergence of 3 causes is what causes SIDS. A vulnerable infant due to possibly some kind of vulnerability, the early stage of development, and outside stressors. So we plan to mitigate the chance of SIDS through anomaly detection of these outside stressors. So this is our team. I'm Alex. I'm the team leader. One second. You can all introduce yourself if you're here.
Hi, I'm Paolo. I'm a software specialist and I'm a computer engineer.
Hey, I'm Christopher. I'm a computer engineer. I'm a hardware specialist.
Hi, I'm Jonathan. I'm a hardware specialist and I'm an electrical engineer.
Okay. So here is our project motivation. So the leading cause of death for infants a year or younger are SIDS and suffocation, with 63% of sudden unexplained infant deaths due to these 2 causes. Unexpected, not explained. Infant deaths due to these 2 causes. And there's really nothing more important to a parent than their child's health. So our device is intended to help detect, alert, and mitigate outside stressors and causes of suffocation. So here's our project selection alternative approaches. So we looked at a few different designs for our sensor, including a sock, a clip-on sensor, remote, and on the ankle. And depending on the comfort, accuracy, and cost of those sensors, we had to decide which one. Overall, we found the ankle would be the best for our system due to it having higher accuracy and low cost.
So as a project summary, we wanted to design a fully functioning baby sleep monitor that would help combat SUID or SIDS. And we wanted to utilize the sensors to monitor the baby and its environment that it was surrounded in. That way we could alert the parents if there were any potential variables or dangers to the baby. So all the collected data would be presented in real time to the parents. That way it could be used to further SUID research. And all parents want is the safety of their child. So this will give them the real-time data or some sort of insight that would better visualize and understand the state of their infant's health. So the system requirements we wanted to focus on was the usability of the system in terms of size, speed, and accuracy. And the product, we wanted to be somewhat simple, yet efficient. So on the right, the chart on the right, you would see the system and the engineering requirements that we required. And then on the bottom, you can see the marketing engineering trade-off matrix with a arrow pointed downward, having a negative correlation between the 2 variables, and then an upward arrow having a positive correlation. The AHP table below shows the 3 important variables that we wanted to measure for our project. So the most important were comfort, accuracy, and cost, with a score being highest for comfort and second would be accuracy. And the breakdown of each category is shown in the objective tree to the right, where accuracy consists of speed and power of the system, and the cost would be between the sensors and the microcontroller. This description of the system is that the sensors would collect data and then they would send that to it would be collected by the microcontroller. and the microcontroller would communicate all of the real-time data to the application through BLE, Bluetooth Low Energy. The mobile application will then perform anomaly detection and send the data to a cloud database for further machine learning analysis, visualization, and storage. And there will be a large focus on mitigating the SUID by detecting outside stressors through anomaly detection. Related theory is deep learning anomaly detection, where an LSTM, also known as long short-term memory recurrent neural network, can be used to understand the sequence of data, and a large enough Euclidean distance between the forecasted and actual value will indicate an anomaly. The precision of the sensors must be taken into account so there are no false alarms from a reading within the individual sensor's precision. So basically, the input, which in this case would be C, would be input, and then it would have a variable X that would affect the output H, and then that output H would then further go into the next input, and it would just go after, sort of all connected in a way.
Okay, so this is the behavior model for our smart sock. We're going to be using 5 different sensors: temperature, motion, sound, heart rate, and oxygen concentration levels. Those are going to go through the microcontroller to the mobile application, and then the mobile application is going to be just communicating with the cloud database to store the information and process it. And for the functional decomposition of our project, basically we're looking at an 8-volt power supply right now. Still working on that. And basically the information is going to go from the sensors to the microcontroller through the mobile application, and then again it's going to go from the information is going to be processed in the mobile application, and that's going to be communicated to the cloud base, and it's basically going to be back and forth from there. This is how our application is looking at right now. We're using Android Studio and Android Studio Developer and with Java. We plan on using Bluetooth connection and cloud database anomaly detection, and we're going to implement that next semester. This is to the right. You can see that it's just going to have a summary in the first page of the application, and that's how it's looking right about now. For the hardware design and implementation, all our sensors were tested, and the code was reworked to help make them consistent with their output. I'm going to be working on Bluetooth implementation for over the winter break and into next semester. And we're working also on a final design with a circuit for all the sensors to be connected to the power supply. This is an example of one of our testing result charts and its analysis. This is the heart rate and oxygen concentration sensor. For this one particularly, we were using the Arduino microcontroller to test the sensor rather than the microcontroller we're using for our actual project, just because it made it easier with quarantining and everything. We found that the Arduino microcontroller didn't have enough dynamic memory, so that caused a problem with stability and it like outputting consistent results. So we're gonna upgrade. We might see how we can upgrade that in our actual microcontroller we're gonna use for the project. We had to alter some of the coding for the heart rate sensor to make it more consistent, but we needed more. We found out that we need more dynamic memory for the oxygen concentration part of a sensor.
So for our go no go milestone for this semester, it was to purchase sensors and microcontroller, testing all the sensors, improve the code for each sensors, create an application, and design a data analysis, which was achieved. Over the winter break, we plan to connect all hardware components, the design a reliable circuit with a power source, and set a Bluetooth connection. And then over the spring semester, we plan to implement a cloud database, refine hardware form factors, add application alerts and data analysis, and then conduct final testing for the final product. Shown here is the cost analysis and the bill of materials, which all comes down to a total cost of $42.49. Although in the future we may need to reevaluate this due to upgrading the microcontroller and potentially buying more parts for the final circuit. So in conclusion for this semester, we have learned the importance of communication and splitting large tasks into doable tasks. And we need to progress making sure every individual has their own task to do instead of shared tasks to increase efficiency. As for future work, it was previous to connect all hardware components, integrate it all into a final circuit, implement Bluetooth connection, implement a cloud database, and do final testing for the final product. Some of the standards that we used in that we followed in our project included the IEEE 802 for Bluetooth implementation and ISO 14882 for C++ code for microcontroller. And some of the constraints that we had to abide by was ensuring that a hardware size was efficient and minimal to fit on an infant's ankle, and ensuring that the microcontroller had enough memory for the sensor coding. On the right side of the slide is shown the IEEE Code of Ethics. Our project followed all of them, and it had a specific emphasis on the 9th statement, which stated to avoid injuring others, their property, reputation, or employment by false or malicious actions, rumors, or any other verbal or physical abuse. This 9th term is especially important to us since we have to ensure that the child's health and ensure that they're not injured in any way, shape, or form. Shown here are some of the references that we used for our project.
Okay, thank you. So, any questions from audience?
Yes, I have a question. I saw the machine learning part. You connect different sensors. Now, it's good to put some basic, just 1, 2 slides regarding the physics of the sensors. You're using different sensors. Keep notes, please. You have a pressure sensor, temperature sensor, different kind of sensors, put some physics, and also the statistics, what kind of statistics you are looking. Okay, so try to implement this part to show that really you have integration of physics and math and statistics with other. Now it's missing this part, and it's very so it's not, doesn't reflect the potential of this study. Okay, so involve the physical part, the statistical part, what accuracy you are looking, etc. Thank you.
Thank you, Dr. Yarkos.
Thank you. It's helpful.
So good morning, everyone.
Morning.
On behalf of my students, I would like to thank everybody for coming and